Hello, in today's presentation, we'll be discussing the feasibility of 3D printing organs. In today's presentation, we'll not only discuss the economic feasibility of 3D printing, but also the technical, legal, and environmental feasibility of 3D printed organs. First, I would like to begin with why we are looking into 3D printing organs. According to the Health Resource and Service Administration, there are over 104,000 people on the national waiting list for a transplant. However, only one-third of these patients will actually receive a transplant. This is because there's not enough uh, willing organ donors to treat all these patients. Additionally, even if someone does agree to be a donor, there's no guarantee that the patient's body will accept the organ. And in some cases, these transplants can lead to acute rejection. 3D printed organs have the capability to save lives by relieving the shortage of organs available. Additionally, 3D printed organs are made using the patient's own cells, which makes it very unlikely that the patient's body will reject the transplant. Finally, these organ transplants could cost less than a life-sustaining machine, such as a ventilator or dialysis. So how does 3D printing work? First, cells are collected from a patient. These cells are grown and multiplied in a lab. Once enough cells are grown, these cells are combined with alginate or gelatin to create a paste-like substance known as bioink. This bioink is then loaded into the printer. The printer builds up the ink layer by layer until the organ is created. Finally, the printed product is taken to a bioreactor so that the cells can mature and become a finished organ. So here are two examples of a successful organ transplant. The patient on the right had an ear created using cells from her left ear. On the left, we have a bladder, which was created in a 3D printer. This bladder was then successfully transplanted to an 11-year-old patient. Although we have made several leaps with bioprinting, there are also several major roadblocks to major organ transplants. The first problem is the number of cells. Hollow organs such as the bladder do not require a lot of cells, so they are easier to create. However, when it comes to complex organs such as the kidney or heart, they require much more cells. To create a heart, we need approximately 2 billion muscle cells. Growing this number of cells would require huge facilities and constant feeding and monitoring, which can cost more than $5,000 a day. Another problem is that complex organs require cells to do complex functions and communicate with cells around it. While scientists are able to create heart and kidney cells, they're not able to replicate the communication that happens between these cells. For example, scientists at Boston University were able to create a 3D printed heart. However, it's only the size of a rabbit heart. Additionally, this heart cannot beat at the same speed regularly as a normal heart because the autorhythmic cells of this 3D printed heart can't communicate effectively and beat at the same time. As a result, while simple organ and tissue transplant may be possible, such as a bladder or a skin transplant, life-saving transplants, such as a heart or kidney transplant, aren't yet possible with 3D printing.
Yes, so after our extensive research, we found that the economic feasibility of our project shows to be very expensive. Initial investments needed to kickstart a project like this can be around $336.5 million, along with other capital expenditures such as facilities, inventory, and equipment. For instance, getting rental office spaces in Solana Beach, California can be approximately $4,000 per month, whereas inventory and equipment can scale up to $3.5 million. Fixed costs will set us back $150,000 annually, with most of it being allocated to personal salaries and the acquisition of professionals like biomedical engineer and radiologists. The remaining amount will be divided to cover expenses such as software licenses, facilities operational costs, printer maintenance, and unexpected purchases. Regarding organ production, it is necessary to opt for selective laser sintering 3D printing to manufacture complex organ systems. However, 3D printers in this category can be worth up to $300,000. Once this technology is acquired, then the production of functional organs using bioprinting can range from $280,000 to $300,000. It is evident that to reach the goal of creating functional 3D printed organs, one must spend a significant amount of money. Unfortunately, early stage companies like Organovo, who developed functional 3D printing human tissues, have found themselves to struggle in accomplishing profitability. Despite the company spending a whopping $302.3 million back in 2021, they have yet to experience any revenues. This alone tells us that the production of 3D printed tissues, which are crucial for the development of 3D printed organs, is not profitable. Therefore, going a step further in creating bioprinted organs for the human body will not generate any returns from the investments that we inject into this project.
As far as legal feasibility goes, there are many hurdles within the legality of 3D printed organs. First would be who is liable. So there's a federal law that dated 2016, 23/6/2016, number 180 FC. And this law states that there's limited regulation and where the government cannot regulate 3D printed organs. Now, this then brings up the issue of quality assurance. Who is in charge of making sure that 3D printed organs are up to code, right? And there is no actual set in stone code, but if there was, then who's making sure it is? There's so much risk involved in making sure that the 3D printed organ is up to code that there are many people that are hesitant. Many companies, the government is also hesitant to take charge and quality assurance. And then because of the limited regulation, the issue then comes of commercialization. Now, the 3D printed organ should be an integral part of the human body, and therefore commercialization should be prohibited from putting 3D printed organs on the market as a being sold in a desperate times measure. And in this case, because of this, commercialization is a pretty big issue. Finally, recognition of 3D printed organs as part of the human body is a big issue as well. This is because the recognition of 3D printed organs as part of the human body after someone passes away, who gets the parts? This is because you do not have complete ownership as you do with your own hand, your own heart, your own ear. And this legal issue is a pretty big issue because then otherwise someone can just take one of the parts and just put it on the market, even though it should be the person who passed away's decision in the end. As far as it goes with environmental feasibility, there is additive manufacturing, which leads to a reduction in carbon footprint. Now, because it leads to a reduction in carbon footprint, we can obviously see that it helps the environment. Then we have a reduction in life cycle and material mass. Because there's a reduction in material mass due to additive manufacturing, we have a layer by layer manufacturing system as opposed to the traditional, which is just do all together. This results in less wastage. Then we have a reduction in build time, and that's because, again, of additive manufacturing. The reduction in build time then results in a decrease in energy consumption, which of course is beneficial for the environment. Finally, 3D printing, because of the things it uses to 3D prints, the cells, the bio ink, it's always there. So it has negligible resource consumption. And in that case, it wouldn't ever harm the environment because we're not overusing any type of material.
Now, moving on to the technological challenges, let's consider the challenge of printing complex internally intricate organs. These organs have intricate vascular networks, complex tissue structures, and precise functional requirements. Replacing them accurately through 3D printing is a substantial technological hurdle. Developing self-friendly materials is another major challenge. To create functional organs, the materials used must be compatible with living cells and tissues. Finding and optimizing these materials is a critical aspect of successful 3D organ printing. Crafting an accurate 3D organ model presents another significant challenge. To print an organ that functions as it should in the human body, creating a precise digital model that accurately represents the organ shape and structure is essential. Overcoming these technical challenges is crucial for the continued progress of 3D organ printing, as it holds the potential to transform organ transplantation and improve patient outcomes. Now, about the risks and challenges. First and foremost, quality control is a top concern. Maintaining accuracy, safety, and efficiency in 3D printed organs is a demanding task. Ensuring that these organs meet the rigorous standards required for medical use is a complex and ongoing process. Costs are another significant challenge. The high costs associated with 3D printing technology and materials can act as a barrier for both customers and investors. Finding cost-effective solutions and scaling up production while maintaining quality is a constant concern. Navigating the regulatory framework is yet another formidable challenge. The 3D organ printing industry must cope with complex and ever-evolving regulations, which can vary by region and require substantial compliant efforts. Biocompatibility is an essential but challenging task. Ensuring that 3D printed organs integrate seamlessly with human tissues and immune systems requires continuous research and development. This is a critical aspect for ensuring that these organs are safe and effective when transplanted. Conclusively, the immediate viability of 3D printed artificial organs is hampered by unprofitability, legal concerns, and the insufficiency of current technologies. And these are our works cited pages.